Good morning, friends. Now we are discussing laminar and turbulent flow in module number 3 of the subject fluid mechanics under fluid dynamics. So laminar and turbulent flow. So the fluids what we are having in the real world are viscous. So when the viscous effect is negligible, so the flow will be treated as ideal fluid. Otherwise, the fluid will be treated as a viscous fluid. So the flow in a pipe, so or duct will be classified either as laminar or the turbulent, depending on so the magnitude of the Reynolds number. So the laminar flow will be characterized by the stream smooth and highly ordered motion, whereas turbulent flow is very zigzag. So there will be fluctuations in the velocity and highly disordered motion. So the transition from a laminar flow to the turbulent flow will occur over some region. So in which the flow is fluctuating between laminar flow and the turbulent flow before it becomes fully turbulent. So most of the flows here encountered in the practice will be turbulent. So when there is highly viscous fluids such as the oils flow in the small pipes or narrow passages taking place, so there we can find laminar flow. So we can verify where the laminar flow is existing, where the flow is turbulent, and where the flow is transmitting from laminar to turbulent using Reynolds experiment. So the Reynolds experiment apparatus is consisting of a tank, so to maintain the head. So then a small tank containing the dye, that is the coloring pigment, a glass tube, and the flow regulating valve. So slowly we are releasing the dye into the liquid. So the general arrangement of the setup is shown in the figure here. So we have the tank in which the water is flowing so through the glass tube. So we have the controlling valve here. So the head of water is maintained constant in the tank. So the water flow through the glass tube so is now regulated using this flow regulated valve. So now the velocity of the flow depends on the opening of this flow regulating valve. Now how the flow is happening in the pipe will be observed by allowing a colored dye to flow slowly from the capillarity tube. So which is placed such that the filament of the colored dye will enter the pipe centrally, so that the color dye is entering this glass tube. So at the center, that is at the neutral axis of the glass tube. So Reynolds observed that when the flow velocities are very low, that is by controlling this valve. So if we make the flow of the fluid with less velocity, the dye remains a thin straight line along the entire length of the glass. So the dye filament we can observe here. So that indicates that the flow of water in the glass tube is laminar. So without mixing with water. So the dye is not getting mixed with the water. So there is only thin filament of the colored dye flowing in a thin line separately, not mixing with the water. So such flow is laminar flow. As you slowly, gradually increase the flow velocity in the glass tube with this valve, so a disturbance will start to develop in the dye line, and so it forms the wavy filament. So that is the indication that the laminar flow is transiting to turbulent flow. Now this indicates that the laminar flow has become unstable. On further increasing the flow velocity, so the dye starts mixing with the surrounding water. So this indicates that the flow is turbulent 1. So diffused filament of the colored dye shows that so the fluid flow in the glass tube becomes vigorous. So the colored dye gets started mixing with the surrounding water. So now we have Hedge and paisleys equation. So that is the viscous fluid flow through the circular pipe. So here we are considering a horizontal pipe of radius capital R. So the fluid which is viscous is flowing from left to right. So as shown in the figure. So flow is happening from left to right. So we consider a cylindrical fluid element. So this is the fluid element which is hatched. So that is having the radius small r, right, and thickness gr. So let the length of the fluid element will be dx. So as shown. So the length of the fluid element is dx. So if P is the pressure intensity on the left side face AB. So P is the pressure intensity. So now pressure is, so now taking pressure is equal to force by area. So pressure force is pressure into area. So pressure is P. So area of the fluid element is pi r square or pi d square by 4. So pi r square. So then intensity of pressure on the opposite face CD. So here. So the pressure force in the opposite direction is now P plus del P by del X of dx into pi r square. So pressure is P plus del P by del X into dx. So into pi r square. So on the face CD again is the flow. So now pressure force in the direction of flow is so P pressure into area. So that is area of the fluid element pi r square. Now we have the shear force here. So that is because of viscosity we have shear force because it is said that the viscous fluid is flowing. So we have the shear force. So that is we know that shear stress is equal to force by area. So shear force is shear stress tau into area. So now since it is acting on the length of this fluid element, so we are considering the circumference. So that is 2 pi r into dx. So tau into 2 pi r dx on the surface of the fluid element. So this is the shear force. So now for equilibrium we are taking the summation of pressure and viscous forces in the x direction. So and made equal to 0. So we are getting so shear stress distribution. So this is the shear stress distribution we have to the power of 1. So del P by del X is constant across the section. So shear stress tau is varying with small r. So this is linear. Thank you friends.